All right. Good morning, good afternoon, good evening, if you're in a distant land. I'm Dr. Bill Goodman. I'm both the CEO and CTO for Goodman Technologies. I started the company in Albuquerque, New Mexico in July of 2016. It was 30 days after learning that my 13-year-old boy needed heart surgery and a week after being laid off from my job. And that was the best time to start a business because like you and your missions, I knew that I could not fail. And so I've been in business, it'll be 8 years in July. And we've had 25 SBIRs and STTRs. 9 of those are Phase IIs. I've been a small business person of the year for the SBA's Emerging Leaders Program. Our company has been a New Mexico Technology Council Flying 40 company for the past 4 years. We've had a lot of good success. What I'm going to talk to you about today is our AI-empowered additive and robotic manufacturing, and in conjunction with using the robots, we've created our own ecosystem of nanocomposite materials. So some are printable and some are laminate composites. The key technology that's on the cover page here, we call ANT. It stands for Aligned Nanoforest Technologies. And this is an additive that we put between the layers of a composite in the weakest part of the composite to actually make it the best part of the composite. And I'm going to show you some applications for use in air, space, land, and sea with ANT. On the right side of this cover slide, you'll see the various marketplaces that we're looking at: space, aerospace, hypersonics, healthcare, nuclear energy, and consumer products. And let's see, we'll go to the next slide. So as I mentioned, we do have a track record of being successful. On the right side of the screen, I mentioned the technology Flying 40. We've been mentored by SCORE, which is funded by the Small Business Administration Defense Logistics Agency. I've been in the Emerging Leaders Program. That's how I got to be the 2020 Small Business Person of the Year for New Mexico. We were in the first cohort for the National Security Innovation Network. We were a government showcase company with the Department of Defense, the U.S. Patent Office, and the Small Business Administration at the Eureka Park exhibit of the Consumer Electronics Show in 2022. We've been a Tech Connect Defense Award winner. We were in the Navy's commercialization accelerator program called Navy Launch, put on by H4X Labs. And the most recent, we're graduating as an Igniter Elite company from New Space Nexus, which is a 501c3 that was founded in conjunction with the Air Force Research Laboratory as a founding partner. There's over 200 space companies in that alliance. They have a facility in Albuquerque called the Launch Pad, where there's some capital equipment that I helped specify, and they're doing a lot to mentor small businesses in the space area. So to look at Goodman Technologies, we're doing manufacturing as a service, as well as R&D, and we are also supporting a number of other small companies in doing customer discovery for their products using our printing and our additive manufacturing. And as I mentioned, we've done very well with SBIR. We've had $12 million in undiluted seed funds, We've also had a couple of grants from the state of New Mexico. They call these New Mexico Small Business Assistant Grants. And we partnered with Sandia National Lab 2 times and with Los Alamos 2 times. And right now we have about $3 million in backlog going forward. Today I'm in Albuquerque, but I have locations in Tampa. That's what I call headquarters these days. Albuquerque is now the back office. And we have a nano laboratory in Reno, Nevada, where our engineers are. So these are some of the people that we've partnered with and our customers, whatnot. So down kind of in the lower right quadrant are all the government organizations that we have had SBIR contracts with. So they include an active one with the Space Force. We just completed the Phase II with NASA. For the Air Force, we developed an all-weather shielding for the Air Force Nuke Weapons Center. For the Office of Naval Research, we're making high-temperature composites that can be used in jet engines. With the Army Research Laboratory and RDCOM, we were the first ones to 3D print body armor. We did silicon carbide, alumina, boron carbide, and hybrid of silicon carbide and boron carbide for them. For DARPA, we made some very exotic shielding. And for the Office of Secretary of Defense, the Strategic Capabilities Office, we made some additively manufactured hypersonic projectiles. We've partnered with a number of universities. So University of Hawaii I've been working with for about 13 years. We just completed about 2 years of work with the National Institute of Aviation Research at Wichita State University. I'll show you some of that coming up. We've also worked with New Mexico Tech and the University of New Mexico, and New Space Nexus is a qualified research institution. We have a large partner that's going global in the area of sustainable technologies for energy and recovering critical materials. And that company is called Ghost. Another interested party is Dawson Dynamics, also looking to do a global play. In Taiwan, we have Grand Systems. They make chassis and dispensers for CubeSats up to about 12U. And so along the Rocky Mountain chain, branching off to states on either side of the Rocky Mountains, we're their distributor for those products. In Germany, we have ECM engineered ceramic materials. They make a carbon fiber reinforced silicon carbide that's TRL9 space qualified. Space Florida is a place where we can buy capital equipment. They'll buy it and they'll lease it back to us, so it looks good on our balance sheets. And then down below, we have a number of companies. So Auriga, Exos Aerospace, Space Copy are all small space companies. Hexcel is the last large composites manufacturer that's wholly US owned. GE Aerospace was our first Phase III commercial spinoff. We've had Northrop Grumman and Lockheed Martin as subcontractors. We're continuing to talk with Boeing. And one of our strategic advisors is Nino Marcantonio at Marcantonio Global. And that's about 90% of the people that I can show to you. All right, so what's the big problem? Extreme environments, and that's on and off the planet. And each of these extreme environments requires a next generation solution. And the marketplaces that I showed you on the cover page, they're all huge in terms of total available marketplace, serviceable, obtainable marketplace to Goodman Technologies. So one of our most useful technologies is for shielding. So we make a lead replacement shielding. that's lighter than aluminum or titanium. So it's good for space systems as well as airborne or things on land and sea. We were pretty fortunate with the last geomagnetic storm. Probably a lot of you out there saw the aurora borealis. We even had it in Florida. Unfortunately, I was in a movie theater, so I missed out on all the action. Didn't think it would go that far south. But one of my key concerns, you know, to do a 1-minute elevator type pitch, space. It's not a friendly place. It has extreme temperatures, deadly radiation, debris, and collisions. Space systems engineers, they have to trade weight, cost, schedule, performance, and survivability until now. Now you can have it all if you use your GTNANO products. Another place where we have some significant leadership, even better than in some of the national laboratories, is in the area of hypersonics. And as some of you will know, we're third in a 3-horse race against Russia and China, who already have deployed weapon systems. But there's also need for high temperature materials in spacecraft. As you know, when Artemis came back about 1.5 years ago, large chunks of the spacecraft were missing. And even though it's the same material they used on the Apollo, they didn't formulate it the same way. On Apollo, there were little honeycomb cells that were individually filled by people with a syringe. On Artemis, there's big blocks. So my customer at NASA is actually working with Lockheed Martin to fix that system. But I'll show you that we were the first to additively manufacture a reusable hot structure. And then in the last big area, energy efficiency. So we're working with the Navy to make metal replacements out of nanocomposites to be used in jet engines. So we've also made the composite systems that are used on the F-35 and made them better with our enhancement. We're working with a drone company right now called Naviator, and we can make drones lighter and tougher and less observable with our composites. So there's a number of things we can do, but we basically make the composites lighter in weight, tougher, more survivable. We reduce the scrap, and that's a big part of the cost of using composites in systems today. We also improve upon the manufacturing tolerances. You can now make sharper bends like you have on an airfoil. So I'll get to a little bit of that in just a minute.
Hey, Bill, this is Eugene. So you mentioned that you can make them less detectable. So are you addressing signature issues? Are they just RCS or IR?
Yes.
Vibration?
So, well, I can't do much for you optically, but in the RF domain and microwave, we can do a lot. So the material basically eats up energy across the entire electromagnetic spectrum, from low frequency to frequencies in the deep gamma ray energies. And I'll tell a little more about that, but that's a very good one. So we can take composites like are used on the F-35 or the F-22, which are low observable, and we can make them even better. So that's one of the advantages. This here is what our magic solution is. So we have ported all of our materials and some of our manufacturing equipment, like the printer on the right that's circled in green, to robotic manufacturing systems. And for NASA, we made a 20-inch diameter thermal protection system for spacecraft. You can see that in its various stages there. We're working with carbon reinforced silicon carbide, silicon carbide, reinforced silicon carbide. And we're one of the few companies that can actually take the legacy TRL9 carbon-carbon materials and make them better like they were in the old days of using them. So let me show you why the synergy of nanocomposites and artificial intelligence and automated integration and machine language, when you synergize these, you get an amazing solution. And what I want you to note on these videos is just how fast this is. And what I'm going to tell you is that things that in the past took months to years to build can now be done in a matter of days to weeks. So that video of a fiber patch placement system applying our ceramic matrix composite prepreg that we made on a roll-to-roll basis that the machine then chops and puts onto the substrate. In this case, the substrate is a very high temperature insulation to make the structure both lightweight and very survivable. The next thing that we do is after we've done that insulation, now we're printing on the silicon carbide nano paste. What I want you to notice in this video, we're printing a horizontal, a vertical cylinder on this part. And you notice it's not coming off, it's sticking really good. That is an amazing capability. And I got one more to show you. So we had to go around a transition zone at the edge there where we had curvature, and you can see it's all seamless, and you can see it, on the robot. And like I say, we call this the cake, and this is putting the icing on the cake. If you scan that barcode, it'll take you to a YouTube video that unfortunately, it doesn't really work here because it would shift to another screen and I'd have to sync that screen up. But I encourage you to take a picture of that, take a look at it. It's really, really cool. And this is some of the thing that my AI specialist does. The little figure in the middle of that barcode is me. That's my talking avatar. I have my own talking avatar. It looks like me, it sounds like me, but it dresses a hell of a lot better than me. And with that, let's jump to the next page. All right.
So I'm going to stop you here for a second, see if anybody has any questions before we move on.
Sure, that's a good place.
All right. Any questions? Material
All right.
specs, manufacturing specs, anything? All right, you're good to go. I'm not seeing anything.
All right, so let me tell you about Ant. The easiest way to tell you about Ant is to talk about an Oreo cookie. Everybody's eaten an Oreo cookie. And the strong part of the Oreo cookie is the cookie shell. And the weak part of it is the cream filling. Everybody knows we can twist the two shells and the cookie comes apart and you can get access to that cream filling. Well, laminate composites are the same way. The strong part of the laminate composite or the cookie shell is a place where there's fibers. These can be carbon fibers or glass fibers or silicon carbide fibers, lots of different fibers, but it's the strong part of the composite. But in between the layers in the composite, you have an area called the matrix rich zone. That's the cream filling. There's no reinforcement there. It's the weakest part of the composite. So here's what Ant is. It's an aligned carbon nanotube nanoforest. So let me tell you what a carbon nanotube is if you don't know. We all write with pencils. And the black part of the pencil has always been called lead. Well, it's actually graphite. And when we scrape that graphite along a piece of paper, we're shedding layers of graphene. Graphene is a one-layer construct of carbon atoms, and they're arranged in a honeycomb, just like in a beehive. You have a honeycomb. And at every corner of the hexagons in a honeycomb made of carbon, you got a carbon atom. And every other atom is bonded together. It's double stitched. There's a double bond there. And that's what makes graphene really electrically conductive. In fact, it's more than 10 times conductive than aluminum and double what copper is. And so now if we take a sheet of graphene and we roll it up into a soda straw, we get a carbon nanotube, in this case, a single wall carbon nanotube. You can also have multi-wall carbon nanotubes, and that's what we use primarily in our technologies, the multi-wall. Well, if we now that you've had that Oreo cookie, you need to brush your teeth. So think about a toothbrush. All the bristles are lined up on the toothbrush in rows, and they're standing up vertically out of the handle of the toothbrush. Well, now let's imagine that each of those bristles on the toothbrush is a carbon nanotube. That's a vertically aligned carbon nanotube for us. Now let's also imagine that we've taken the handle of the toothbrush and we've made that out of aligned carbon nanotubes. Those are in the horizontal direction. So when we combine horizontal and vertically aligned carbon nanotubes, you get one of GT's patent pending technologies, the world's first orthogonal nanoforest. And in the picture in the middle, to the left, you'll see a round object that has a line in it. That line is 7 microns wide. That's a single carbon fiber. Now, for comparison, one hair on your head is about 100 microns in diameter. So that gives you kind of the frame of reference for the diameter of a carbon fiber. Now, next to that, you see something that looks like a sky full of stars. Those are all the individual carbon nanotubes that we've added into that matrix-rich zone. So we take that matrix and we fill it up with those aligned nanotubes. And when we do that, it behaves like nano Velcro to hold the layers of the composite together. And this is far superior to some of the other approaches to making composites tougher, which include knitting or braiding. And to prove the point, down below is a table. A pristine composite has none of our technology in it. And we compare those material properties for the pristine composite with one that's been enhanced with our ANT technology, one of the GTNANO products. And you can see that for all of those material properties listed, you get double to triple digit improvements. And in the case of electrical conductivity, it gets over 1 million times better. And that's why this material is useful for shielding against electromagnetic pulse or electromagnetic interference, X-rays, gamma rays. It's also the feature that makes the material a low observable. Now, the cool thing about a carbon nanotube, I told you it's electrically conductive, but it's also almost as hard as a diamond. So we're putting a material that's hard like a diamond into that weak part of the matrix, and that's why we get these drastic material improvements. So that's why we can take something like an airfoil and make the edge, the leading edge on it, very tight. That's going to be extremely important in hypersonics, is you want that to be a knife edge at your leading edge. All right, so let me tell you some of the use cases and why this is value. For the Office of Naval Research, we beat out 5 other competitors to demonstrate the use of polymer composites that were enhanced with a nanoforest. And the key orthogonal property that they wanted to improve upon was increasing the shear strength. And there are a lot of places where the Navy can use some. You'll see some on this page. but a number of them are aircraft like the F-35, the next generation air dominance, but there's also hypersonics for global strike. So those are some of the use cases. But we have demonstrated in a mega matrix of testing that we increase the interlaminar shear strength, the toughness of the material, the fatigue capability. So the Navy's pretty happy. We're about to receive a Navy option phase 2 to do some more prototype development for them. The Navy, we participated in their STP program. And because of that, we were selected by the Navy 4th Fleet. Actually have a meeting tomorrow morning with 4th Fleet and what's called the DONSEC to do an experiment on board a ship in Key West coming up in September with another company that makes drones. We made several material systems for the Navy. So we made the high temperature polyimide, which can go up to about 750 degrees Fahrenheit. That's about 1.5 times the temperature that your kitchen broiler can achieve. We also did bismalimides. Bismalimides, that's what the skin of the F-35 aircraft is made of. And then on the interior of the airplane, there are many epoxy composites. But there are a number of programs of records and use cases here for our composite systems. And PO Subs knows us, PO Ships is taking a look. But there are lots of things where we can make the composites better. Here's an example of some of the composites. We won't tell you what the material property was, but you can see we got the double-digit and triple-digit improvements with these material systems. The value to the F-35 program in reducing scrap, rework, and repair, the bar chart on the right is taken from GAO reports. And this was a program that was coming into production. And the problem is that as time went by, the amount of scrap, rework, and repair was increasing. That arrow is supposed to be going the opposite direction. So when we analyzed, just based upon the double-digit performance improvements that we were getting, we estimated that over the 50-year life cycle of that one aircraft program alone, we could save the government from $400 million to $1.1 billion. Another place where we're impactful with NASA, we showed you the robots making the additively manufactured hot structures. Well, we also tested these at Ames Research Center against a plasma that simulated the conditions of Earth reentry from low Earth orbit or from Mars. And we were the only company that demonstrated a reusable system. We had no weight loss and no erosion. So we combined a superior material with a superior manufacturing process. And you saw just how fast the machine can do this. So the machine also allows for scalability. Another use case where the differentiated manufacturing comes into play is for making CubeSats. So we made a shielding material that was tested by the Air Force at White Sands Missile Range. It was tested against EMP, against X-ray. It was also tested in Dayton against very broad spectrum RF energies. And you can see one of our panels in testing there. And down below is some of the 3D printed silicon carbide mirrors and structures work that we did with NASA. I think we had about 4 phase 1s and 2 phase 2s that addressed making large scale mirrors out of silicon carbide. So we were the first on the planet to 3D print a 100% silicon carbide mirror technology for NASA. We also printed truss structures. So if we combine the mirrors and the truss structures, you can make a telescope. And so we are making a subscale model of that telescope for the Space Force presently. And we're also making a box out of our shielding, which is basically about 2/3 the mass of aluminum. That's going to be thermal vacuum tested the end of this month in Albuquerque at the new Space Nexus launch pad. It's going to be gamma ray tested at the University of New Mexico. And then the material is going to the Cal Davis cyclotron, and it's going to be tested against high energy protons. So that CAD model that you see there is for a 12U CubeSat for doing imaging work. And the advantage of using our composite shielding is it allows you to use off-the-shelf electronics in the space system. And until now, most of your space system electronics have had to been made with very expensive radiation-hardened electronic systems, for which there's only a few foundries. They're very expensive and they're lower performing than off-the-shelf electronics. So now you can use a $3,000 camera with our mass-produced telescopes. Mass production's good because it brings the cost down. And so we can refigure our telescope to user requirements. Some want to look at it in RGB color. Some want to look at it in monochrome. Some want to look at things in the infrared, and some want to look at their targets with hyperspectral cameras. So we've made one telescope that can support all requirements. That gets the telescope cost down by a lot. This particular 12U was looked at by Space RCO, but they didn't have the money to buy 2 of the satellites, wasn't in their budget. But these CubeSats are half of what the Artemis goal is for weight. They're 21 pounds. So we could also provide the solar panels and the antennas and all the other things that go in the box. We pulled together a team of partners in 72 hours to do that for Space RCO.
So, Bill, this is Eugene again.
Yes, sir.
Have you tested your materials against micrometeor impacts?
Not intentionally, but I had something that flew on Missy 6 or Missy 8. It was a silicon carbide mirror. It was flying on the wake side of the ISS, and micrometeorite caught up to it at 17,500 miles per hour, impacted it, and actually left a crater on it. And for anyone who's knowledgeable about silicon carbide, one of its unusual features is that it goes from a solid phase to a gas phase without ever becoming liquid. This micrometeorite impact showed that it actually liquefied under supercritical conditions and then refroze to make the volcanic crater that was on it. So,
so it did stop penetration then?
The silicon carbide actually stopped the micrometeorite. Yeah, it did.
Okay.
So I have the mirror either somewhere in my home or somewhere in my office.
Yeah, if you send me a picture, I'll put it up with everything. Yeah,
I'll see if I can dig that up. So yeah, it was there was a report that I think it was the Navy Research Lab or maybe it was Aerospace Corporation did on it, but that was pretty astonishing. So yeah,
I got a question also from Dennis. Go ahead, Dennis. You got your hand up.
Hey, this is Brian, not Dennis. Brian Andrews from SoftWorks.
Okay.
Yeah, so good to see you guys again. I had a question on how workable your GTNANO stuff is. Can I machine it? Can I drill it? Grind it? How workable is it once it's in its final form?
Okay. So if we're talking about like our additively manufactured armor, there's actually a green state where you can machine it, and it probably machines like wood. Okay. In fact, that's the process we use for making those mirrors polishable. Is we'll take them in the green state, the ceramics, So again, it could be silicon carbide, could be alumina, could be boron carbide, and you can machine things there. And we've made our material a low shrinkage system that once you do fire it and convert it to ceramic, you haven't, you might only have a little bit of touch machining to do. Now the laminate composites, they're highly machinable, same as any other composite. So all we've done is made the composite better in terms of its materials performance. So you can still drill holes in it for vias or whatever. You can bond in inserts like Invar or Alvar. Yeah, you can bond things to them. In fact, at the state of, let's see, next week in Albuquerque is the State of Space Industrial Base presentation. We'll actually have our 20-inch part there. But yeah, I think we have something in Vulcan. We made one of the cards for some of the additive. But I'm in Tampa. I can always drop by and see you guys.
I'll set something up after this. I made a note to put you guys in touch.
Yeah, that's it, Bill. Yeah, thanks for the answer. Appreciate it. I know some of these, fancy composites, right? They're really hard to work with, or you need you got to get like professional help to drill a hole in it. And so I just wanted to be sure, this wasn't some kind of stranger to them. Now, I appreciate it. I know you guys are local, so yeah, thank you very much. Appreciate it.
My pleasure. My pleasure.
So how many more slides you got, Bill?
Not too many.
Okay, because we're down to about 5 minutes. So
perfect. This is a big commercial application, wind turbines. This is a place where we would need to generate over 1 million square feet of material a year. And this is a company that's going global, Ghost. Let me tell you about our team. Mathis Shinnick is our CFO. He grew up on Wall Street. He worked for all the major investment banks. He then went to Europe and did merger and acquisitions, then went to the Far East, and he's back in New Mexico. Our most recent partner here is John Vo. John Vo set up the first 3 Tesla model automobile factories and the first Gigafactory. John's also in Florida, and he and I are going to partner with Wichita State University, and we're going to create a GTNANO factory. And Mike Whitmer, if you do scan that code and look at that AI stuff, he's the guy that does it. The guy is a Mensa. Ron Unruh's our COO. He's on the telecon today. He was the first duly warranted officer in the entire Department of Defense. We've got lots of great advisors. You can't beat our people when it comes to space. I even have a hedge fund manager, Cody Willard, who was on Fox Business, the Jay Leno show. He was a talking head on CNBC. Here's why you want to work with Goodman. In 5 years, we're projected to do about $1.4 billion in revenue. We have these various market verticals that we're pursuing in both consumer goods as well as the dual use aerospace and space. This slide shows you how we go about that scaling. So as we bring different products on board, we need to have more reactors to make our material. And this gives the investors an idea of the capital investment that's required. So it's actually phased in time. You don't have to make a big lump sum up front and then worry about if we're going to be in business or not. And so we're looking to make an exit, whether by M&A or an IPO in the 2029 to 2030 timeframe. We're looking for $2.5 million. NASA will match that $2.5 million with the Civilian Commercialization Readiness Pilot Program. And then where there are some other government entities that can even match those monies to make it better. But the first 2.5 gets me some help, some additional engineering, business development people. the special tooling that I need to do the customer discovery for all the people that want to try this. And there's legal, there's more intellectual property to get secured, and get some more people in the C-suite, what we call the succession team. The name of the new company, the spin-off, will be GTNANO Incorporated, because that's our registered trademark. And with that, my famous closing statement is, when you need nanocomposite materials for extreme environments, you better call Goodman. Thank you so much.
All right, so it's opened up for questions. So Brian Crowley, you came in late.
Hey,
Dennis?
yeah, this is Brian again at Softworks. I'm going to jump in real quick. Bill, have you looked at the Air Force's TACFI? That's that tactical finance money.
I'm familiar with TACFI and StratFi. Basically, what we need is a customer that has pull and has a requirement that we can fill, and then I think it's I won't say it's easy, but we have a number of investors that want to be like the second or third investor, but the lead investor, the one that breaks the ice, has been the hard one for us.
Okay,
just because of the CapEx. Does that make sense?
Yeah, it does. I would think that Space Force would probably be a good customer, and then TACFI it. But if you're aware of them, yeah, I'm not telling anything you already know. So. Yeah,
no, it's TACFI is a good amount of money. A StratFi would get us everything that we wanted to do. So, yeah, there's also Title III right now too. So we're in a new consortium called DIBC, Defense Industrial Base. So I'm hoping we get some pull there.
All right.
I must have done a really good job, because nobody had questions besides Dennis.
Yeah, I guess. So now I saw you had a picture of the 1000 up there, and I worked signatures at NSWC Carter Rock.
Oh, small world.
Yeah, so I worked RCS, IR, and EO.
Okay.
Are you working with them at all, or?
So the closest we come to Carter Rock right now would be through the NSTXL OTA. But the one that's
actually out of Crane.
Yes, that's right, Crane, right. No, Carter Rock is, I think they're just discovered who we are through, it's the cousin of Softworks. What is it called? Is it
Naval
Nautilus?
Yeah, Nautilus, right. I'm in contact with Nautilus as well.
Yeah, so Nautilus met me at Sea, Air, and Space a couple of weeks ago. We've had 2 telecons, and I believe the hypersonics folks are interested in what we're doing, but I haven't had the poll yet.
Okay, well, I can put you in touch with Air Force and Space Force Futures, unless somebody is here from there that wants to chime in. But right now I got Jeremy Tootin. He's got his hand up.
Yeah,
you want to go ahead?
I did come in a couple minutes late, but I heard you talking about some shipboard experimentation. You talked about the qualities of your materials. I'm curious about how thin you can deploy a layer, and I'm kind of thinking about the RAM that they put on Gen 5, Gen 4 aircraft to lower their signatures. I'm curious if you could deploy on ship to replace the material they use, or recode an aircraft, or repair a damaged section.
Oh, yes. In fact, we submitted an SBIR to the Navy. We didn't get selected for it, but we can actually make a patch kit in conjunction with companies that actually do aircraft repair, and put together a kit that could be done on. So the Marine Corps has a large amphibious or an excursion system where you can land an aircraft that needs repair. I think one of the big problems we have in an exchange in the Pacific is there is a lot of anti-aircraft. There are going to be a lot of aircraft that have holes in them, they'll be able to get back to a carrier and land, but then you're going to have to patch them and get them back up in the air. So yeah, we could make a low observable patch material using the Bismally image that would allow them to basically patch, cure, and get the airplane back up in the air. Absolutely.
All right, thank you for that, Jeremy. Did you have anything more, Jeremy?
Every other question that I thought of, he managed to answer before I could get to it.
Okay, great.
Thank you.
All right, so anybody else have anything right now before we move on?
Well, thank you so much for this opportunity to speak to your forum, Eugene. I really appreciate it an awful lot, and I've enjoyed our conversations.
Yeah, no, I think this is going to be you're going to see a lot of opportunities come from this. So, okay, Brian, yeah, I was hoping Brian would chime in. Go ahead, Brian.
Hey, Bill, I just want to say thanks for you putting this on. I missed a good bit of it. I apologize. I'm out in Idaho at a gold mine, but I'll shoot you an email and see if we can keep doing stuff with the basalt composites with Nick Gencarel.
Oh yeah, basalt has got a lot of promise. It's an amazing material, and I'm just frankly astonished that it hasn't become more pervasive in the industry.
Yeah, we're working closely with basalt. Brian has set up at least 24, 25 opportunities through the forum, working to get them to present on the benefits of the basalt. And that was one of the questions. So what you do with so carbon fiber is that's manufactured. That's not a natural existing structure,
Yeah,
is it?
and it's something that it's manufactured. It's something that is now people are trying to recycle it and recover the fiber because it's really durable stuff. And the basalt is nice because you can it's an insulator. It's good for high temperature. It's basically melted rock.
Yeah.
Yeah. And you can make armor. So we could actually combine some of that material with our additively manufactured thing to make large strike plate for vehicles, for buildings. Yeah, there's just a lot of places where I can take a material like that and I can make it better.
All right. Well, I'll set up a call for you, me, and Brian to talk. But we're running about 10 minutes over here, so I want to give Ed a chance. You can hang out if you want, Bill, if you have the time, or you can check in at around 2:15, 2:30 to answer any questions that people might have, or we can continue discussions.
Yeah, I'll come back at 2:15. That'd be great.
All right. Thank you. Appreciate it.